Today we will start an example of dynamic programming. So the name of the problem is that matrix chain multiplication. Okay, the name of the problem is matrix chain multiplication. Means there are a series of matrices which are to be multiplied. Okay, now in which order you should multiply so that the cost of the multiplications will be minimized. This is the problem. So you see that you know the basics of matrix. So there is an n by m matrix. Suppose it is A. So Aij is, so it is two-dimensional matrix. Okay, you know these are the entries A11 A. This is the first row A11 1 2 1 dot, 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 up to m. Then second row, third row, nth row. So it has n rows and m columns. So it is still the order is n by m. You know already this. So example of 4 by 5 matrix is this. Okay. This is the 4 by 5 matrix. Is it visible to everybody? I think. Hello.
Yes, sir. Yes, sir.
Okay. So this is the 4 by 5 matrix. Now you know also the product. The two matrices can be multiplied if the number of column of the first matrix is equal to the number of rows of the second matrix. For example, C, A and B are two matrices and their multiplication is C, and A is of order P by Q and B should be of order Q by R. Means the number of column of first matrix and number of row of the second matrix should be same, otherwise it cannot be multiplied. Okay, and the resultant matrix C will be of order P by R. Okay, the rows number of rows of first matrix and the number of columns of the second matrix. This is the matrix C. So mathematically we can write the each entry of the matrix C is denoted by Cij, which is equal to the sum of the products Aik and Bkj, where k varies from 1 to I. Okay, you know all this. Now you see that C has, you know, P into R entries, because you see P by R. How many rows and how many columns? Number of rows is 5, P, and number of columns is R. So total number of entries will be PR. Now each entry is obtained by multiplying the rows and columns of elements from rows and column of A and B. So where each entry, and that takes how much time? Theta q times to compute each entry. Each entry means this one. Okay, this is the each entry. It needs how much time? K equal to 1 to k equal to q. Okay, q, this q. So that means you are multiplying. See here, one multiplication, two multiplication, another three multiplications, q multiplications. So you need theta q times to multiply and then sum. So each entry takes this amount of time to compute. So the total procedure is, see, for one entry it needs theta q. So p for PR entries, p into r into q. So that means theta pqr. So entire procedure it needs this. For example, you know, if A and B are of order n by n, then time needed to compute this matrix is theta of n cube. That you know. Okay. Now see here, A is this matrix, B is this, C will be this. You know, basic mathematics. Now matrix multiplication is associative. That means whether you are multiplying first these two matrices A1 and A2, then A3, or whether you are multiplying first these A2 and A3, then with resultant with A1, the result will remain same. It doesn't change. Result is same in which it is irrespective of the order. Okay, so the parenthesis does not change the result. Final value of this multiplication will be same, but it is not commutative. That you know, that A1 into A2 is not equal to A2 into A1. Now say a matrix A P by Q, B is Q by R, and C is R by S. So the multiplication these can be computed in two ways. Either you first multiply this AB then C, or first BC and then with A. So number of multiplications needed are how much? if you do like this, first you are multiplying AB. Okay, so if you multiply AB, the resultant matrix will be of order P cross R, because P R. Okay, and then you are multiplying with this C. Clear? So to multiply these A and B, you need P Q R multiplications. Then you are multiplying this resultant with C is R into S. Okay, so if you multiply this, then it will take PRS. So you total number of multiplications for in this case is PQR plus PRS. Is it clear? Next, if you multiply B and C first, B and C, then you see QRS it will take, because the result is resultant matrix is Q cross S, and it takes QRS. Then you are multiplying with P, this A, P by Q. So it will take PQS. So the number of multiplications needed in the two cases are different, although the value of the final matrix is same. We are not interested to know the final matrix. We are interested to know in which order we should multiply the given series of matrices so that the number of multiplication is minimized, whether this one or this one. Now you see, if there are three matrices, okay, fine, you can do like this. You compute this, then you compute this, then you take the minimum. But if there is a series of matrices, n number of matrices, A1, A2, A3, then in which order you should multiply? That is the question. So here you see, for example, if A is of order 5 by 4, this is 5 by 4, this is 4 by 6, and this is 6 by 2. So if you multiply in this way, then it needs 180 multiplications. But if you multiply in this way, 88. So there is a big difference, number of multiplication. And you know now number of multiplication operation is costly. Okay. So our objective is to reduce that number of multiplications. So how can we do this? So that means parenthesization is important. You please see in which order you are multiplying this. So you know already this problem, that multiplication means parenthesis problem is stack permutation, means catalog number. So dynamic programming will be used. So here, suppose we have to multiply this A1 to AN, given this is the multiplications, means just series of matrices A1, A2, A3, AN. N matrices are given. The dimension of A1 is P0 by P1. Dimension on its order of matrix A2 is P1 by P2. Its is Pn minus 1 by Pn. So that means you see this P0, P1, P1, P2, P2, P3 in this way. So that means you can put it in a vector, one dimensional row, means like this. First one is P0, then is P1, P2 in this way up to Pn. So given dimension P0 to Pn corresponds to the matrix sequence this, in which AI has the dimension or order Pi minus 1 by Pi, that is that I was saying that A2 has the P1, P2. 2 means P1, P1, 2. N minus 1, 2. So that means AI has Pi minus 1 by Pi. Now you need to determine the multiplication sequence, in which order you should multiply these matrices, which matrices should be multiplied first, then which matrices in this, so that the minimum number of scalar multiplication is minimized. Or in other word, in which order you should parenthesize the multiplications. See, 4. So anyone can do first these two, or someone can do this like this way, or someone can do this, or someone. So in which order you should multiply so that it takes minimum number of means minimum multiplications. It needs minimum multiplications. You know this is the Catalan number, na? You already know that Catalan. It is Catalan number of parenthesizing. So that
Yes, sir.
means 2ncn, we have already proved this. So this is 2ncm is this exponential. So if you yeah, so if you try to multiply everything in this way, and means in this series, in this way, in this way, so and finally you take the minimum, it will be exponential. Now you may think that is a np hard problem. No, it is not np hard problem. There are some other techniques so that you can handle this, means in polynomial time. So what is that? That is dynamic programming. Now define space of sub problems first. See, optimal problem is you need to multiply to find out the minimum cost multiplication and sequence for a1 to an. A1 to an means which? That means a1, a2 to an. This is the given. So this is denoted by a1 dot 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 n. So sub problem means, what do you mean by sub problem? So forget about 1 and n. Suppose I have been given a sequence like this: ai plus 1, ai plus 2, okay, aj. For these, can you solve this problem if I ask you? So that means for every pair where I is less than equal to j and I is greater than equal to 1 and this is less than equal to n, this determine the minimum cost multiplication sequence for this. And I am denoting it by this a I j. This is this. Okay, enter minimum for sequence for this. So now this is the final matrix aij. It will have the order pi minus 1 into pj, means this. I know that this is of order pi minus 1 by pi, and this is of order pj minus 1 by pj. So final matrix will be order of order pi minus 1 into pj. Now there are how many sub problems are there? NC2, obviously I and j can be selected, means two. I need to select two index I and j. So NC2 and square such sub problems are there. Okay. Now here you will see, if you try to compute everything, that means say 2 5 you are computing. Sometimes you are computing, means this is 2 5 means a2 a3, I am saying a5 up to a5. Now if anybody computes like this a1 to a7, then you see this is the subset a1 to a7. It has subset a2 to a5. So if you again compute for these here, then that will be a wastage of time. So better you have to, I said in the last class that the essence of dynamic programming is that you need to store the result for the smaller sub problems, so that you can fetch that in future again if it is required. Okay. So that is the way to solve the larger problem using sub problem solution. So at the last step of any optimal sequence or for a sub problem, there is a k for some k such that two matrices, the series ai to ak and ak plus 1 to a are multiplied together. That means you have been given ai, ai plus 1 dot, 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 up to aj. So what you are doing, you are parenthesizing this. That means you will compute this one first and you will compute this one first, and then multiply these two matrices. Say this is, suppose this is b, and suppose I am saying this is c. Then finally you will multiply b by c to obtain aij, ai dot dot j. Okay. So now where you are doing this partitioning, where you are doing this, you are taking this from this to this. Why you did not take it here, this partitioning? That means this to this and this to this later. So that means there is some rule. Okay. So how do we decide where to split the chain? Where is the, what is the k? So can be any k. So we need to check all possible values. Now how do we parenthesis the two subchains aik recursively na? Ai to k, again you have to partition it at some point here. Again you have to partition this k plus 1 to j. So that partitioning gives you that parenthesizing. Now you see, if you have multiplied these optimally and if you have multiplied these optimally, okay, then you will get this also and optimally. Means if this series has been multiplied optimally, and it has been multiplied optimally, then there is a chance to get optimal answer for here. But suppose it has not been multiplied optimally, means then there is means you are getting larger answer, larger values to multiply ai to ak. Then how can you expect that ai to aj will be also, you for this sequence of matrices you will also get the minimum number of multiplications? That means to get the minimum number of multiplications for the series ai to aj, you need to obtain the minimum number of multiplication for the series that you have generated by splitting the entire series of matrices. Okay, so how can you do that? This is the our task. So that we are saying that if the optimal value involves the splitting it into aik and ak plus 1 to j at the final step, then of parenthesization of ai to k ak and ak plus 1 to aj in the optimal solution must also be optimal. That I was saying. If already I said that if aik ai to ak is not optimal parenthesization of, then it can be replaced with cheaper parenthesization that you have not generated, yielding a cheaper means minimum value of multiplication, so it will not give the minimal. Similarly, AK plus 1 to AJ sequence should also be optimal, means parenthesization of this in which order you should multiply, that should be optimal. If you uh, could not parenthesized the expression AK plus 1 to AJ, then it is not optimal, then you will not get optimal answer for AI to AJ also. So you have to find out the optimal solution for the optimal sub problem also. If you do not get the optimal solution for the sub problem, you will not get the optimal solution for the given main problem. Okay, now how can we do this? Suppose for means we know that I for I equal to greater than equal to 1 and less than equal to j to n, let mij denote the minimum number of multiplications needed to compute aij. So this is the value, this is the value, minimum value, to find out, I mean, how many multiplications are required to for the series ai to aj, that is mij. Okay, so these optimal costs must satisfy the following recursive definition. This mij will be equal to 0 when I equal to j, that means when only there are one matrix, suppose a5, only one matrix, so it will not be multiplied with anyone else. So in that case the number of multiplication is 0, I is equal to 0. But otherwise ai means obviously j should be greater than I. In that case what I have to do, see here, this sequence ai plus 1 dot up to aj, so it should be, it should be split into some portion, say here. Okay, so that means here is ak and here it is ak plus 1. So this series ai to ak and this series ak plus 1 to this j, so you are splitting at this position. Now these k values here, it can be here, it can be here, it can be here, it can be here, any position. So that's why k is from I to less than j. Okay, and how many multiplications are required for this mi to k, because I know mij is the minimum number of multiplications for the series of matrix ai to aj. So for the series of matrix ai to ak, the number of multiplication will be mik. Similarly for this series ak to plus 1 to aj, these will be the multiplications. Now here you see ai to ak and ak plus 1 to aj. So this is of order how much? First one is of order pi minus 1 by pk, and the second matrix, this one, the second matrix, this is the first matrix of order this, and second matrix is of order pk by pj. Now if you multiply these, you will get ai to j. So I have obtained the number of multiplication for this and for this. Now you will multiply these two. matrices. So how many extra multiplications will be required to multiply these one and these one? That pi minus 1 into pk into pj, that we already know. So total number of multiplications to for aij, if I split here like this, it will be at these positions, then it will be m k plus 1 to j, and then pi minus 1 into pk into pj, this. Now k may be, k not be here, k may be at some place, so that's why you vary k at different positions, and you find out the product of all those all so sum of the products of sum of the series, sum of these value for all values of k, and take that value of k for which it is minimum. Clear? Yes or no?
Yes, sir.
Hello.
Yes, sir. Yes, sir.
So now this is the proof that I have told already, that this there is no multiplications, and I have to optimally means split, and then I have explained all this. Okay. Now how to how, in which order I should compute, in which order we should compute. So this will be the bottom of computations that I told. In dynamic programming, always you try, see, don't say that there is a table, means if there is a table where I am storing the value, then that will be dynamic programming. No, you should have computed the solution for smaller sub problem, store it in a table, and while computing the optimal value for the larger problem, larger size, then you will, instead of computing the solution for the smaller sub problem, you just will fetch the result from the smaller sub problem, the table. This is the essence. Somebody says that okay, there is an array you are storing, that is dynamic programming. No, not like that. So bottom up computations, now that means here fill the, see, mij is a table, it is a table like this, I varies, j varies, so this is the mij. Okay. So in an order such that when it is time to compute this, the value of mik and these are already available, that I was saying that for first smaller values you compute, then for the larger values. So the order is like this, that easy way is to compute in the increasing order of the size, j minus I. J minus I means if j minus I equal to 1, so that means m1 2 m2 3 m3 4 mn minus 3 to n minus 2, then n minus 1. So all the single valued uh, entries are computed first, then the difference should be 2, that means m1 3 2 4 3 5, you check the difference is 2, 1 to 3 2 to 4 2 3 to 5. Okay, then 3 1 to 4 2 to 5 3 to 6, and in this way finally you compute n minus 1 size, and then m. I need this one, the minimum value to multiply the series of matrix from a1 to an. Yeah. So basically this is from, this is, you see, this is from for a1 a2, check it, this is for a2 a3, please remember, this last one is for an minus 1 into an. Similarly, when there are these two, it is an minus 2, an minus 1, an. First one is a1, a2, a3. This is a1, a2, a3, a4, like this. So you see, first I am computing the series like this: a1, a2, a2, a3, a3, a4, adjacent. Then a1, a2, a3, a2, a3, a4, a3, a4, a4, 5. In this way. Okay. Finally, a1, a2 to an. So take an example. See, I know it has order p0. This is order of order p0 by p1. This is p1 by p2, and this is p3 sorry, P2 by P3, and this is P3 by P4. So P0, P1, this is the order. Find M14, the minimum number. So initialized what? You see P0. Here you check. This is the M table. Okay. This is that M table. This is the I, J. Okay. Now here you see P0 is this one 5. P1 is 4. You check it. The given value is this. And these are the matrices A1, A2, A3, A4. Right. Now here you see this is 0. Why? Because here you see in this case this is I equal to 1, j equal to also 1. Check it, this 1 1. This is I equal to, you check, it is 2, it is 2. So here I2 j2 same, so that's why this is 0. So similarly I3 j3, these are zeros. Fine. Now computing M12 first. So by definition M12 is this. So this will be 120. Check. M11 is 0, M22 is 0, and P0, P1, P2. 5 into 4 into 6, 120. So this I is 1, you check, this is I, and J is 2. So this is 120. I have computed. Then we will compute which thing? This one. Then I will fill up this one because these are the size of 1. You check 1, 2 minus 1. Then this is 3 minus 2. Then this will be 4 minus 3. In the same way, you compute. This will be 48. This will be 84. Now size becomes 2. That means so I have computed the number of multiplications for, see, this is for A1, A2, this is for A2, A3, this is for A3, A4. Now we would like to compute for A1, A2, A3. That means here, and A2, A3, A4. So this is basically the length. You can see length of the sequence of the matrices 3, here 3. It was length was 2, 2, 2. So for 2 I have to use this formula, just k values where you are splitting. See, check it, A1, A2, A3. Now here there are two possibilities. Either you take k equal to 1, that means here, or you take here. Here. That means here what happens? Basically A1, A2s are multiplied. Okay. Then you are multiplying A1, A2 and then A3. Here what happens? First A2, A3s are multiplied. Then you are multiplying with it A1. Clear? So these are the difference. So this case is for here and this case is here. This for them. You check it, k value, k. So in this case you take compute all this, okay, and you will get, see, P0 into P1 into P3. P0 is this, P1 is this, 5 into 4 into 2 means 40. So you add with this 40, what do we get? And in this case also you take the minimum one, 88. So that's why it is. And where you are getting minimum, that is also important. That will help you to find out or reconstruct the parenthesis. So here similarly A24, this is also computed. In this case it is like this, A2, A3, A4. This meaning either there are two possibilities or there are these possibilities. 4. Here also the same thing. You see, when while computing this, we are taking the help of these entries. You check it, 2 to 4, 3 to 4, this. We are not computing. This has been already stored in the table in the previous iteration. In the following next iteration, while the this size increases, we are not computing the solution for the sub problems. Sub problems, you see, M24, it has been already computed. Where? You check it, M24 is this. I sorry, not this. Uh, this one. This is 2 and this is 4. This is the M24. This is the M24. So I am not computing here. I am just fetching the result from the table. Okay, now I am computing it. Final, which one is the minimum, and I am storing it. So 158 will be the answer. Okay, so Mij only keeps cost, but not actual multiplication sequence that I told. In which order you should multiply. For that, you should take another table. Okay, Si to j. That means AI, AJ, sorry, I plus 1, AI plus 2, AJ. Now, where you split, suppose you are splitting it here, K. So, what is that value? That you store in this case, K. This will help you to reconstruct. Suppose means S A1, A2, A3, A4. In this case, suppose I need to first split here so that I will get the minimum. So that means this is 2. So here S1 to 4, it will be 2. This gives the value of K where I should split. Means I will get like this. I should this. So Sij is K. That K is the index that achieves the minimum in this case. So you need to maintain an array. Okay. Where Sij denotes K for the optimal splitting in this case. So how to recover? That you should check the value of the tables in from the Sij, and then you should use. For example, consider n equal to 6 and assume the array this constructed. So if S16 is 3, that means you please remember while you are computing M, then you should update the value of S also. When you are getting Mij, you are getting means you are updating the final value of Mij, then you are sure at which value of for which value of K you are getting the minimum value of Mij. So let that value be 3. K value is 3. Then you should store it 3 in the Sij table, means S16. So here you see, for example, S1 to 6 is 3. So that means A1 to A3 means A1, A2, A3 should be split, and A3, A4, A5, A6 should be multiplied. A1, A2, A3, A1, A2, A3 should be multiplied, and then A4, A5, A6 should be multiplied like this. Now I should check A1 to 3 means S1 3 and S4 6 also. Suppose S1 3 is 1. That means I need like this. After 1, the multiplication will be like this. And S4 to 6, suppose it is 5. So that means A4 and A5 should be multiplied first, and then 6. Okay. So the final sequence is like this. Is it clear?
Yes, sir.
So this is the essence. So and what will be the algorithm? This is the algorithm. In this case, you see, for I equal to 1 to n, Mij is 0. Okay, I do not know the M tables first. So, and here II is 0. That means I know that this one will be 0, this one will be 0. Why? Because A1 and A1 means self multiplication is 0. Basically, this. Now, L means what? Please remember this L stands for length. length of sequence of matrices. It is meaningful. So you are computing first two. That means A1, A2, A2, A3. Okay. For A1, A2, A2, A3, A3, A4. In this way you first compute. Then L value will be 3. A1, A2, A3, A2, A3, A4. In this way you will compute. So for I equal to 1 to n minus L plus 1, where you will means this varies from, you see, I equal to varies from n to n minus length plus 1, obviously. Otherwise, you will not get final length. Means the sequence is split like this, and j will be the index just after I plus L minus 1. I plus length minus 1. So initially 2 here. So 2 minus 1 means 1. So I plus 1. When I equal to 1, then j will be 2. When I equal to 2, j will be 3 in this way. And mij is infinite. You take very large value, means as possible in the entry. Now, if we see that it is possible to update, we will update it, minimize. So for k equal to I to j minus 1, then you multiply this. See here, k value can take I to j minus 1. You see the formula that we have seen in the dynamic programming. Mik plus this, and if this value is less than mij, this, for example, infinite, automatically it will be updated. So you update it, and you also update the sk table, sij, that I was telling. So finally you will return the m and s tables, optimal mean. So this takes how much time? This takes of order n. This for loop also of order n, and this for loop is also of order n. So n cube. So here you see this is polynomial. Okay, it is not exponential using dynamic programming. So whenever you will get some very large value exponential like, then you should try, is it possible, you should try, if it is possible, not always, that can you design the algorithm, any algorithm for the problem in polynomial time using dynamic programming approach technique. If it is, means if you can do, then fine. Don't say immediately it is hard problem, you need to prove it, then hard problem. For you it may be hard, for others it may be easy, means they can design in polynomial time. So I stop here. Do you have any query?